Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Jessica Sunshine with us today. Hey, Jessica.
Hey, how are you?
I am doing well. We are on July 15th, 2021. And in Phoenix, it's going to be a little toasty today. We'll probably get up to about 41. A little humid because this is when Phoenix gets its rainy season. So summer is when it rains and when it gets a little humid and all that. But I'm doing quite fine today. And where are you, Jessica? And how goes
I'm in Maryland, in my home, actually, because it's still COVID stuff. And I got used to being in my home, so here I am.
There you go. That is it's a pretty awesome background picture for your home there. What is that comet?
Yeah, well, home in the sense that our universe, that is the comet Ison, which you might remember was approaching the sun very close to Thanksgiving a few years ago.
Mm-hmm. Yep.
And it's just a beautiful ion tail. It's just one of my pretty pictures of comets. We got lots of them. One of my favorites.
We're going to be talking about one today. So yeah, very good. I like that a lot. Let's see, July, Maryland. Are you getting the 17-year locust?
Oh, come and gone, but it was really intense.
Yeah.
Really intense. We measured it was actually 3 decibels higher than standing next to my lawnmower.
So yes, they are amazing. I was well, who cares? Date myself. I was 10 years old and living in Virginia when one of those 17-year locust things came through. They're pretty intense. There are a lot of locusts.
Yeah, we just now have some, I guess, for lack of a better word, carcasses.
Right.
Around. Yeah.
Everywhere. Everywhere. But I was surprised. I was talking with somebody the other day, and apparently they don't go very far north, right? Like they were not up in the Boston, Massachusetts area.
No, I don't even think parts of New Jersey.
Yeah.
It's very localized, and it was very localized here, depending on how many trees people had and microclimates, things like that. So,
wow, very good.
We had plenty.
Nice. So, Jessica, what do you like to do for research?
Well, I'm a spectroscopist, sort of at my core, and I'm very interested in compositions of planetary surfaces.
Cool.
And that's taken me from, meteorites in the lab and to the lunar surface to comets, asteroids for sure. So solar system bodies, but really focus on composition.
Very cool.
Most of the time.
Nice. I like compositions. I like making them. And that is going to bring us to this very lovely Planetary Science Journal, PSJ, the AAS Journal's newest publication, referee journal article. And we have all comets are somewhat hyperactive and the implications thereof. And Jessica, take us away.
Well, first of all, I have to say that this was very much a partnership with Lori Figi. So I'm sitting here, but much of everything you're seeing in the article, we did together. And that was actually really one of the highlights of my summer, doing that together. Yeah, it's an interesting story. When people hear hyperactive, they think, Ritalin, right? The comets are perfectly well behaved in that sense. But what it literally means or was referred to is the concept that you can have a comet that's seeming to produce more water than its surface area, or nearly so, right? It's not a strict definition, it's the right kind of thing. So you've got these beasts that are producing a lot of water given their size. And it was first discovered in a comet called Wirtanen, which came close here a few years ago. And we've done a lot of studies. But was actually the original target for the Rosetta mission. So people spent a lot of effort trying to understand and document Wirtanen, and that's sort of where the story starts.
Right.
And as it turns out, there's a handful of these, they're all pretty small, like kilometer-sized nuclei, that we would call hyperactive. Again, there's no rigid definition, but one of them is a comet called Hartley 2. And for everything we knew from remote observations, and still know actually, they're twins. You know, they're the same size, and they have this excess, way more water production than any of the comets we visited by spacecraft, which are much bigger and frankly wimpier.
Yeah.
Okay. So, so we've known for a while that these are interesting things. And, you know, when you have something that behaves differently, it's bound to tell you something about fundamentally about comets in general. So I should also say that this story is very much a story about Micah Hearn, who I can say I had the privilege of working with and who was a mentor for many years and really was a pillar of the cometary science community, but also was very involved in the publication board of AAS. So I was really excited to get this paper into the new PSJ. So that seemed really appropriate. We had this issue of what's causing this hyperactivity, and there were lots of theories, from stuff falling off the nucleus, big things, little things, who really knew, some excess source of energy that was producing maybe water on the, not related to sun. That was, you know, and usually that's attributed to amorphous ice transitions. Right. If you want to make up some energy to use amorphous ice. Very much unknown, totally unconstrained. I hope people recall there was this mission called Deep Impact, and we did a really successful impact experiment to the Comet Tempel 1. And we found ourselves, which is a whole other story, but we found ourselves with a working spacecraft with a working spectrometer in particular, and wanted to do an extended mission. And Mike had always wanted to go to Hartley 2 because it was interesting, and we, of all the places we could go potentially, it was high on the science list. But it turned out it would take us 2 or 3 years longer than some of the other targets, and we didn't think we'd have financial support for that. So we set course for a comet called Botan, which you probably have never heard of, because we soon realized that we didn't know where Botan was. We couldn't recover it. And so we literally, I was the deputy PI at that point, Mike and I went to NASA and said, hey, we're sending your spacecraft to nowhere. Can't find the comet. But we were grouped, and there was lots of support at headquarters, and we got to say, okay, can we now go to Hartley 2? And we did. Lots of support at JPL for trying to figure out how to make that happen, and to make it happen in a way the spectrometer could work at the right phase angles and all that good stuff, not trivial. Right. And after a lot of work, we did it, several lunar Earth flybys, and we got to Hartley 2. And one of the things we saw right away, which is in this first figure, the bottom right is a bright little area, is just the edge of the nucleus, and everything you're looking at is off the nucleus. Yeah. And so you're seeing what should be black, dark sky, completely black, as we've seen everywhere else with this instrument. And what we're seeing in this image is, in fact, all these little tiny point sources. We can't resolve how small they are, but they're acting like point sources. And we know that. I don't know if you can blow this up or not, but if you did blow it up, you would see that there's little rings is what you're seeing. It's not, and that's because the telescope was out of focus. So every single point source turns into PSF, turns into ring, which in this case was really great because we knew we were seeing individual things and not anything else going on. Turns out to be the ice grains.
Yeah. What is that's what I want to ask. What is the size scale here? I mean, is this?
Oh, you're asking a question I no longer can answer off the top of my head. I'm sorry. I have to go back and look. That's okay. But what you're seeing is not individual ice grains, but clumps of ice.
Okay.
Yeah, that's probably was your question. Yeah, we're not resolving anything, but it should be dark sky. That's the point. And so we have visual evidence that there are bright things, likely ice grains sitting off the nucleus in the coma. Okay. And now if you go to, I guess it's figure 2. All right. Look myself. Yeah, which is on the next page. So this is a modification out of Mike's science paper, which really set up what we've termed here the hyperactivity model. A lot going on here. So on the upper left is an image of the comet itself. And on the right are three spectral maps. And if we start on the upper right in green, so you're going from the color scale is such that, bright is more. You can see there's concentration of CO2 vapor coming out of what we call the small end of this nucleus. Huge concentration of CO2. And the one on the right, sort of an aqua color on the bottom right, is a map of, the one on the right.
Yep, sorry.
There you go. Is a map of water ice. So the 3 micron ice absorption. And you can see there's very good correlation between the CO2 and the water ice.
Yeah.
So the very first conclusion is that it seems that CO2, which is more volatile, is dragging ice out of the nucleus, right? And you still have water ice. Yeah. And I always like to say, if you go to the bright blue one, which is water vapor, we almost didn't do it because we just assumed it was near the ice. And what is very interesting and a complete surprise is that you can see there's a concentration. There's water vapor everywhere, but there's a concentration at what we call the waist between the 2 lobes of the nucleus. So you have this excess water vapor coming out. And what Mike hypothesized at the time was that, okay, the CO2 ice is coming out, CO2 is dragging water ice out. Some of those grains are going to be moving slowly enough that they're going to fall back. And in fact, we could trace a few of them, about tens of them, to the gravitational low. They don't escape, even though this thing is only a kilometer in size, you don't escape the gravity well if they're going slow enough, and they fall back.
Okay. And
the gravitational low is the waist. And you can see the waist is visually smooth, and it is where we're then seeing subsequent water vapor. So this at the time was really exciting to see this kind of complex interaction on a comet, and not to mention what I would call and did call a sedimentary process where you're moving material from one part and it's redepositing on the other. We would never have guessed that this was happening. So there's 2 really important things from here. One is that you're dragging water ice into the coma. It eventually will sublimate and provide a second source for water ice. So that explains in a nutshell, where did the water, how do you get so much water? Well, you have all these small surface area things sublimating on their own in the coma, and in addition to the nucleus. So you can get a high volume of water vapor over time. But secondly is this fallback issue. That material, it's going up and the stuff on the surface is not pristine. It's gone out, it's thermally evolved and reprocessed. So that's the basic model. And if you go, I think it's figure 3, kind of conceptualize this in a way that hopefully taking all that data makes sense. Right. So what happens is the CO2 is coming out. That's kind of that triangular region there schematically. Some of the water ice that's coming out with it. So it's coming out from depth in that little insert. You have CO2 at depth dragging out water ice and presumably dust. Some of it falls back on the surface, as we discussed. But the stuff that does escape actually is then subject to solar wind pressure. And that solar wind is going to drag it to the anti-sunward spot, the opposite side of the comet, where it will submit. And that is actually the secondary source we were looking for.
Okay.
So schematically, that's sort of what, based on all that data we had there. And I should just mention that the fallback was an idea, right? It was a concept, but we didn't really have evidence for it as a community until Rosetta. And it was quite clear that this kind of process of fallback and distribution of material was happening on even that relatively inactive comet. So we subsequently sort of had proof that this process was happening.
Nice.
Okay. And if you jump to figure 5, I think was probably worthwhile.
Yes.
What you're seeing here is a water vapor map. Again, the color scales change. Bright is more, white is more, blue is less. The little cross is the nucleus. Okay, so now we're in a remote sensing mode from the deep impact data, and we're monitoring the comet from as we not at close approach, but when we're farther away. We can't resolve it at this scale.
Okay.
But you can see that the earlier time, which I can't remember without looking, 2 hours is the left, and 6.5 hours after closest approach is the right-hand image.
There we go.
Very different water distributions.
Yes.
And what's unusual is for a comet, you would expect if it's coming from the nucleus, it would all be in the sunward side, which is the right-hand side in this data.
Yeah.
And you're seeing that there is, in fact, a very large anti-sunward component in the water vapor. It's very asymmetric, and it actually changes as the comet rotates.
Yeah. Mm-hmm.
So this was proof that what we were seeing, we saw the ice, but now we're seeing the results of the sublimation.
Yeah. Very cool.
And that's actually a topic we're still pursuing. We have a lot of detail here. We're trying to model pretty, we think it's about 40% of the water vapor is coming from the coma, but these data with more analysis will actually provide a real number there. So we're working on that.
Okay.
So I think that was the last of the figures, but so what this would have been interesting, really just a footnote of more stuff than we had learned from deep impact encounter days. But the point is this process of more volatile gas dragging out less volatile ices, it should happen in every comet. There's nothing particularly special. The issue is how much, right? How much comes from the nucleus and how much is being dragged out. And the question is, what kind of gases? In our case, Hartley 2 was CO2. It could have been CO, but you could also imagine that you could have CO2 ice being dragged by something more volatile, like CO or methane.
Okay.
And so you have this concept that, there's no reason we don't, again, the proportions may change given the comet, but this may happen more than we think it happens. Not just with water ice, but all sorts of ices. And so there's this complex feeding mechanism between the nucleus and the coma that we really hadn't recognized before, and we now really need to consider. And as we start seeing from a remote, telescopic perspective, we're going to see asymmetries, sunward versus anti-sunward, in a bunch of different volatiles. And that's what we're looking for, and we've had some evidence as well. And the other issue is this material movement and sedimentary processes actually has an interesting implication. One of the things that was found by a colleague named Liss was that if you look at the D to H ratios, these hyperactive comets are among the most Earth-like.
Okay.
So why? And I think we've shown here why. The ice that comes directly from the nucleus and gets pushed off to be the secondary source is frozen when it left. It was actually inside CO2 gas. It is cold.
Right.
It has not fractionated whatsoever. It represents what's inside the comet.
Okay.
The stuff that we measure that's coming from gas, water vapor that's sublimating from the surface is in fact thermally altered, and it could easily change the D to H ratio. So if you look at comets as a mass, this two source thing also could explain, you could think of it as an H-rich and a D-rich sources. And the more H-rich one you have in these coma-driven populations is going to have the most pristine and perhaps the most legitimate, honest representative of the unfractionated material.
D-H, yeah.
And that drives us to the conclusion that, if you want to sample, we have this concept someday that we want to sample cryogenically, right? Comets, because that is among the most pristine material we'll ever get. It's the closest thing to molecular gases we're going to get. Not a trivial thing to do, especially if you have to drill into somehow a comet to get into the interior where you have the real unfractionated ices. Well, it's interesting to think that maybe this gas drag of material into the coma is doing us a huge favor And the placed sample, if you want to get water, for example, would be that secondary source in the coma, which is just sitting there.
So, yeah.
You don't even have to contact the nucleus. And if you imagine going to farther out, you might be able to sample CO2 ice or methane ice that's doing the same thing, just it would be farther out.
Right.
So that was sort of an exciting thought that all of this stuff affects, what we're ultimately think of comets as being as pristine. Well, they're not entirely pristine. They've had a lot of activity going on that changes certainly their surfaces. So those were the principal drivers of this. And, I think the bottom line is that Mike's concepts, what we call the Mike's model, really suggests that we have to think not only about how we interpret what we measure telescopically, but what we might want to do in terms of sample return, because otherwise we might just bring back stuff that's not what we think it is.
Yeah. Okay.
Oh, that's the paper, I think, in a nutshell.
Very nice. Very nice. And Jessica, I want to thank you so much for sharing your lovely article with us. And I want to touch a little bit. I want to sort of give it a future look here, have you give it a future look. So you mentioned it a little bit, that possibilities of sample returns. So people are generally, over the last year or so, been busy writing white papers for decadal surveys and this kind of stuff. Got it. So is there sort of plans in the work to maybe do a sample mission? And if not, what are some of the other activities going on that can help us resolve if all comets are hyperactive? Are there additional observations? Is there theoretical calculations, et cetera? So just where do we kind of go over the next, let's say, 5 years or so?
Well, in 5 years, we're not going to get a new mission, I don't think.
Probably not. They take longer time scales.
But certainly there is two things on the comet.
Okay.
Decadal survey kind of issues. One is surface sample return, so-called, at least in the last decadal. Mm-hmm. And I think what this work, I hope, reminds people that has value, but to remember that you are looking at a process surface. I think looking at processing is really, really important. I'm actually a geologist by training. So I think that's good, but we have to remember that it's not what we're talking about. And if you're really driving to those frozen, pristine gases, or frozen, ices, I should say, then I think, this is just an alternative that we should think about. We have lots of challenges in that world, not the least of which is, how do you bring back a sample at cryogenic temperatures? Mm-hmm. If you did, what would you do with it? Yeah, okay. And I think that's still, that's a challenge, and we're getting better at it, but it's certainly not in the next 5 years. Okay. Where I hope this thing does have implications in the next 5 years is, as I mentioned, in the telescopic world, where we're, with JWST coming along, and we're going to resolve things at a much better spectral and spatial distribution than we had before, is to look at those data. We used to, I'm sure other people in the field have heard the concept of a spherical cow, right? That's the model for a nucleus. It's a spherical cow. That's the best we can do. It's decidedly not spherical. Right. The emissions are not simple. And now we have to think about how the nucleus and coma interact and how we interpret not just the shape of the nucleus and its rotation rate and its seasonal behavior, all of which are real. But now we've added this other component that we're really maybe seeing two processes at some level. The little bit of hyperactivity can really drive different results. Mm. So I hope people think about that as they're looking for data. And so far people have started to, so that's great.
Awesome. Very good.
Yeah.
Thank you, Jessica. And thank you, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.